Welcome back, everyone, to another deep dive. This time, we're going to be looking at neural audio compression.
Oh, yeah. Neural audio compression.
Which, is going to be really important to all of us as we move into the future with all of our high-fidelity audio and all this stuff.
Yeah.
We're going to be looking at two specific papers.
Okay.
One is high-fidelity audio compression with improved RVQGA, and the other is SNAC, multi-scale neural audio codec.
Right.
Both of these papers are really, really new, and they have some really amazing findings.
Yeah, they're hot off the press, so it's going to be fun to break it all down.
Yeah. So maybe you could start by just telling us, what is neural audio compression?
Right. So neural audio compression basically uses these deep learning models to compress audio in a way that traditional methods just weren't really able to do.
Deep learning. Everyone says deep learning, but what is a computer actually learning when it's compressing audio?
So it all starts with these things called neural networks, which are these complex algorithms that are sort of inspired by the human brain. And these networks can be trained on just tons and tons of audio data. And they can be trained to recognize patterns and figure out how to represent sounds in a much more compact way.
Okay, so it recognizes these patterns, but then how does it actually squish the audio?
Right.
What is it actually doing to the data?
So the main concept here is that it takes a complex sound wave.
Okay.
And transforms it into a much simpler code, a simpler representation. And this is kind of like a blueprint. And then that blueprint can be used to reconstruct the sound, hopefully without losing too much detail.
So it's finding shortcuts to describe the sound.
Exactly.
Okay, got it.
Yeah, and then to make that code as small as possible,
Yeah.
we use something called vector quantization, or VQ. And you can think of this as being kind of like a dictionary of predefined sound snippets
Okay.
that are called codebook vectors. And instead of having to store the entire sound wave, the model can just pick the closest matches from this dictionary and just record the corresponding entries.
So it's like finding these pre-made sounds and just saying okay, put this one and put this one in.
Yeah, exactly.
It's like a shorthand almost.
Yeah, like taking notes in class.
Got it. Okay, so that's how it does it. But what are some of the challenges that people run into when they're trying to do neural audio compression?
Right. So the main challenge is how do we maintain this high fidelity audio quality?
Yeah.
Even at extremely low byte rates.
That makes sense.
Yeah, it's like trying to fit a grand piano into a backpack. And you want it to come out on the other side sounding just as good.
Right.
So the amount of data involved, the complexity of these sound waves, and then just the risk of these annoying artifacts.
Yeah.
These are all things that make this a really challenging problem.
Got it. So how do these papers that we're looking at, improved RVQGN and SNAC, how do they try and tackle these challenges?
So let's start with improved RVQGN.
Okay.
And this paper really tackles that fidelity challenge head on with a technique called residual vector quantization, or RVQ.
Okay.
And basically what this method does is it compresses the audio in stages.
Okay.
By focusing on the residual.
The residual.
Which is like the differences between each stage.
So you're compressing the differences.
Exactly. Yeah, it's like peeling back layers of an onion and compressing each layer.
Got it.
And what's really crazy is the results of this, they managed to compress 44.1 kilohertz audio down to a tiny 8 kilobundercast.
Wow.
Which is a compression factor of over 90x.
That's crazy.
Yeah, it's insane. It's like taking an entire music library and fitting it onto a device that could previously only hold a couple of songs.
Really? That's amazing. But okay, so they're compressing it this much, but how do they keep it from sounding bad?
Right.
I'm always thinking about those artifacts that come with compressing audio, that kind of tinny sound or whatever.
Right. So they address this on a number of fronts.
Okay.
One of the key innovations here is the use of a periodic activation function.
Okay. A periodic activation function.
Yeah.
What is that?
So remember how I talked about vector quantization being like a dictionary?
Yeah.
Well, imagine if that dictionary was specifically designed to understand repeating patterns. Which are common in audio signals, right? So that's what the periodic activation function does.
Okay.
It helps the model to recognize the cyclical nature of sound waves, which results in a more natural and artifact-free reconstruction.
So you're kind of giving it a cheat sheet.
Exactly.
On how audio works.
Yeah.
Got it.
They also tackle something that's called codebook collapse, which is a problem that often happens in these models.
Codebook collapse.
Yeah, so basically, sometimes in these models, only a small portion of that codebook dictionary actually gets used,
Okay.
which limits how efficient the compression is.
So you've got this whole dictionary
Yeah.
and you're only using like 5 words.
Exactly.
Yeah.
Yeah, it's like having a huge vocabulary and only using like 5 words.
Okay.
So they use some techniques to ensure that the entire code book is being used,
Right.
which maximizes the compression potential.
That makes sense. So they're basically making it smarter about how it uses those shortcuts.
Exactly.
Cool.
Yeah. And another interesting thing is that this model uses something called quantizer dropout,
Okay.
which allows a single model to handle different byte rates, which makes it super versatile. However, this can sometimes lead to a drop in quality.
Okay.
But improved RVQGAN, it actually includes a method to mitigate this,
Oh, okay.
which ensures a high quality even at those lower byte rates.
That's impressive.
Yeah.
But how does the model, like, how does it actually know if the audio that it's compressing is good?
Right.
Like, it can't hear, right?
So that's where something called discriminators come in.
Okay.
And you can think of a discriminator as being like a super critical listener whose job it is to compare the compressed audio to the original and point out any flaws.
Okay.
So basically, the model learns from this feedback and it constantly refines its encoding and decoding processes
Okay.
to produce a result that sounds as close to the original as possible.
So it's like a back and forth. The thing is compressing it, and then this other thing's like, no, that's not good enough.
Yeah,
And it has
yeah.
to try again.
Exactly.
Okay.
And in improved RVQGAN, they use a multi-scale and a multi-period discriminator,
Okay.
which means that it analyzes the audio at different time resolutions and different frequencies. And this ensures that the compressed audio sounds perceptually similar to the original, even at those super low byte rates.
That's really, really cool. So that's the RVQ. But now what about SNSC? What makes this one different?
Yeah. SNSC takes a different approach
Right.
called multi-scale compression.
Multi-scale compression.
Yeah, and you can think of it
Right.
like having different levels of zoom on a map.
Okay, yeah.
So you can see the big picture, like the major highways.
Yeah.
But you can also zoom in and see the smaller details,
Gotcha.
like the individual streets.
So how does that apply to audio?
Right. So SNAC compresses audio
Okay.
at different time resolutions, meaning it can capture both the fine-grained details
Okay.
of the sound wave
Uh-huh.
and the longer-term structure of the audio.
Oh, that's interesting. So it's like
Yeah.
it's seeing the individual notes,
Yeah.
but also like the whole song.
Exactly. That's a great way to put it.
Okay.
Yeah. It's like packing a suitcase where you have to like carefully fold some clothes and loosely roll others
Yeah.
to make everything fit perfectly.
Okay.
So by capturing these different levels of detail,
Mm-hmm.
SNAC can achieve really efficient compression
Okay.
without sacrificing the quality.
Yeah, that makes sense. This paper also mentioned some pretty interesting innovations like a noise block
Right.
and depth-wise convolutions. Can you talk about those a little bit?
Absolutely. So
Okay.
the noise block is all about injecting a controlled amount of randomness.
Wait a second.
Yeah.
Adding noise makes it sound better.
So think about it like this.
Okay.
A little bit of controlled chaos can actually make things sound more natural.
Okay.
It's like adding a touch of vibrato to a singer's voice,
Mm.
or like slight variations in the tempo of a performance.
Okay.
It kind of introduces this subtle human touch
Gotcha.
that makes the reconstructed audio sound less robotic
Yeah. Okay.
and more expressive.
That makes sense. What about the depth-wise convolutions? What are those?
So they're a little bit technical,
Okay.
but basically they are a technique that's borrowed from image processing that helps to make the model more efficient
Okay.
and more stable during training.
Okay.
So it streamlines the whole data processing pipeline.
Gotcha.
So everything runs smoother and faster.
So it's like a brain boost for the model.
Exactly.
Hmm.
And on top of that, SNNC also uses what's called a local windowed attention mechanism.
Okay.
And this allows the model to focus on specific parts of the audio signal. Just like our ears can kind of tune into certain sounds
Yeah.
and filter out the background noise.
Okay.
So it helps the model prioritize and
Yeah.
reconstruct the most important features.
Got it. So, okay, we've talked about all these fancy techniques.
Right.
But like, how do they actually perform?
Right.
Like, how do improved RVQGA and SNSC stack up
Yeah.
to the other methods out there?
So the results are really promising.
Okay.
both papers show that these new codecs outperform existing methods, even on these objective metrics.
Objective metrics.
Yeah, so like, for example, they use things like VSQL.
VSQL.
Yeah, which stands for Virtual Speech Quality Objective Listener.
Okay, so it's like a computer listener that's judging the quality of the audio.
Exactly.
Got it.
So it measures how natural and clear the compressed audio sounds to a human.
Okay.
They also use measures like SISDR and Mel spectral distance,
Okay.
which basically you can think of as being like different types of rulers for measuring how close the compressed audio is to the original.
Yeah, that makes sense. Wait, okay, those are all like numbers and stuff.
That's right.
But what about the real world? Like, do these codecs actually sound good?
Yeah, so that's the most important question.
Right.
And the answer is yes.
Okay, good.
Both research teams conducted listening tests,
Okay.
and people were really impressed.
Okay.
They found that these new codecs sound remarkably close to the original audio,
Okay.
even at very low bite rates.
That's what I like to hear. So this is all really fascinating, but I'm trying to think, like, what does this all mean?
Right.
What are the real world applications for this?
Right.
Like, what could we use this for?
So that's where things get really exciting. Imagine a world where you could stream lossless audio, even high-resolution tracks,
Okay.
without worrying about using up all your data.
Oh, so I could listen to, like,
Yeah.
my favorite music in the best quality.
Exactly. Exactly. So that's the promise of neural audio compression.
Okay.
It could drastically reduce the bandwidth needed for streaming,
Okay.
and it can make high-fidelity audio accessible to everyone.
That would be amazing.
Yeah, so no more settling
Yeah.
for compressed audio quality
All right.
just to save data. You can finally enjoy every nuance and detail
Yeah.
of your favorite music,
Right.
wherever you are.
That would be a dream come true.
Yeah. And it's not just about music.
Okay.
Think about voice assistants.
Right.
Right now, most of them rely on really heavily compressed audio,
Yeah.
which is why they often sound a bit robotic.
Yeah, it definitely feels like you're talking to a machine.
Exactly.
Yeah.
So with neural audio compression,
Uh-huh.
we could have voice assistants that sound incredibly natural and human-like
Okay.
without requiring massive amounts of data
Right.
or processing power.
Yeah, that makes sense.
They could understand us better,
Uh-huh.
respond in a more nuanced way,
Yeah.
even engage in more meaningful conversations.
Okay.
It's all about making technology feel less artificial.
I like that.
Yeah.
So what about other areas? Are there other things we could use this for?
Absolutely. Think about the gaming industry.
Okay.
As games become more and more immersive,
Uh-huh.
audio quality becomes increasingly important.
Right.
So neural audio compression could enable developers to create incredibly rich and detailed soundscapes
Okay.
without having to worry about these huge file sizes
Right.
or bandwidth limitations.
So to hear like every footstep and every like rustling leaf or whatever without any lag or glitches.
Exactly. So it could take gaming immersion to a whole new level.
Wow.
Yeah.
The possibilities are kind of endless.
Correct.
But are there any downsides to this technology?
Right. So you're absolutely right.
Yeah.
With any powerful tool, there are always two sides.
Right.
One concern is the potential for misuse,
Okay.
especially when it comes to creating things like deepfakes.
Deepfakes.
So
Get those videos where it looks like someone's saying something that they didn't actually say.
Exactly. But in this case, it would be audio deepfakes.
Audio deepfakes.
So imagine audio recordings
Okay.
that sound so real that it's impossible to tell they're not genuine.
Yeah. That is, that's a little scary. Like you could ruin someone's reputation pretty easily with that.
Exactly. So it's a serious concern.
Yeah.
And we need to be really mindful of the ethical implications as this technology advances.
Okay.
We need to develop safeguards to make sure that it's used responsibly.
Makes sense.
Yeah.
Like any powerful tool.
Exactly.
You gotta be careful.
Exactly. But overall, the future of audio is incredibly exciting.
Yeah.
It has the potential to completely revolutionize how we experience sound.
Yeah, I agree. So where do we go from here?
Right.
What are some of the big questions that researchers are looking at now?
Yeah. Yeah, so one of the good questions is, can we get to perfect fidelity at 0 byte rate?
Oh, wow.
Like, can we just shrink audio down to practically nothing
Okay.
without losing any information?
So like the holy grail of audio compression.
Yeah, exactly.
That sounds impossible.
It's a huge challenge.
Yeah.
And there might even be fundamental limits to, how much we can actually compress information.
Right.
But maybe we'll find some totally new ways of, representing sound that we haven't even thought of yet.
Yeah, I really like that about this field.
Yeah.
It's like, you never know what's going to happen next. Another area I think is really cool is like how neural audio compression and AI kind of work together, especially like generative AI.
Yeah, absolutely. Generative AI, it's all about creating new content and, specifically audio experiences.
Right.
Whether it's music or sound effects or even like human voices.
So you're saying like we could use AI to make totally new sounds from scratch.
Yeah. Imagine being able to generate any sound you can imagine, just using AI.
Wow. So how does neural audio compression fit into that?
So it could play a really big role in making those AI-generated sounds much more realistic and, more expressive and more accessible.
Okay.
Because right now, AI-generated audio, it can sometimes sound a little artificial.
Yeah.
It's missing that, certain something.
Like that human touch.
Exactly.
Yeah.
So neural audio compression could be that missing link that helps to bridge that gap and unlock the full potential of generative audio AI.
So like we could have AI writing symphonies that sound like a real person wrote them.
It's definitely possible.
Wow. Or like sound effects for movies.
Yeah.
That sounds so real, it's like you're actually there.
Exactly.
Boy, that's amazing.
And, on a more personal level,
Okay.
imagine being able to create your own personalized soundscapes.
Okay, yeah.
So you could filter out unwanted noise, enhance the sounds that you do want to hear,
Okay.
and even like tailor your audio environment to your specific mood
Oh, wow.
or preference.
So I could like block out the city noise
Yeah,
and just hear like birds chirping or whatever.
exactly. It's about taking control of your audio experience, making sound a much more integral part of how you interact with the world around you.
It's almost like we could change our reality with sound.
Yeah, you've hit the nail on the head. The future of audio is not just about the technology. It's about how those advancements change the way we think about sound. It's a fascinating journey, and we're really just getting started.
Well, this has been an awesome deep dive. I feel like I've learned a lot.
Yeah, it's been great talking about this with you.
And to everyone listening out there, make sure you stay curious.
Yes.
You never know what amazing new sonic experiences are waiting for us